start by reviewing some of the different symmetries. I'll show you several geometries, most of which appeared in the notes for reading assignment 5. And for all those symmetries, I'm going to discuss what kind of symmetry is present, and I'll sketch the field and also show you what a good choice of Amperian contour is for applying Stokes' theorem. Now let me remind you that Stokes' theorem looks like this. You have your contour integral of a vector field is equal to the flux of the curl of the vector field F through the surface S, where the surface S needs to have the same orientation as the contour by the right-hand rule. So your fingers would align with the contour and your thumb should align with the normal vector to the surface. Now in most of the problems, I mean actually in all of the problems for this topic, you will be given this J, or you'll be asked to find J, for example, which is the curl of the vector field F. So your problem setup would look like the governing equation would look like this. This would be the right-hand side and this would be the left-hand side. Okay, let's discuss the geometries. For this case, this is a slab. Your vector field would look something like this. So all of those currents would produce the field that would go based on the right-hand rule. You would imagine aligning your thumb to the current and your fingers would curl around this current density, producing the field like this. On a trace, this would look like this. Your F would go in the negative y direction here and positive y direction here. And then inside the contour also something similar will happen, right? Okay, so a good contour for this case is a contour that will capture J, so it would have a normal vector that's parallel to the direction of the current density. And also, another feature of a good Amperian contour is that the contour aligns with the field on some of its portions and is perpendicular to the field on the other portions. This makes everything much easier to integrate. The kind of symmetry that's present in this problem is planar symmetry, and is discussed in section 4.1. The next kind of symmetry is, well, geometry is like this. You have a cylinder. You see the way I drew the current. This is not a shell. This is a cylinder with some sort of volume current density, current flux density. The field produced would go around this cylinder like this. Again, by the right-hand rule, your fingers would align with the field and your thumb would align with the current. And then here it would look something like this. A good Amperian contour is, again, the one that captures the current density. So it would be a circle in this case. In this case, the symmetry is cylindrical because nothing depends on theta and nothing depends on z. And the only sort of important variable in this case is the distance from the z-axis. And the kind of current that we have here is the axial current flux density. There is another option. The reason why I'm specifying the kind of current density is because in a cylinder, you could also have a situation like this, where the current is flowing circumferentially. Okay. So, and this is discussed in section 4.2. In section 4.3, you have geometries like this one. This is an infinite axial helix. This infinite helix. The kind of current density you have is circumferential current flux density because it goes sort of around the circumference instead of going like it did in this problem. The field produced would be like this. The field produced, you could imagine aligning your thumb to the current density, and as a result, your field would go like this. Now, I want to mention there will not be any field outside of this helix. We had a discussion in tutorial 8 about why this is the case and why it's a very good assumption to have this. Here, this is how this looks like. This is the field. Field outside is 0. And the contour you would set up would again capture your current density. You could set it up in either counterclockwise direction on this trace or clockwise direction on this trace. It doesn't really matter as long as you're consistent and very careful. Yes. And this is discussed in section 4.3. Also in section 4.3, there is a bit of discussion about other kinds of cylindrical geometries where the current is circumferential. One of those would be when instead of this helical kind of geometry, you just have a sheet of current. That's another possibility. You could also have, which I'm not showing here, you could also have shell with current that's not thin. So you would have some sort of thickness to the shell. And then instead of surface current, you would have a volume current density that's distributed over some volume. But that's not what I'm showing here. Here I'm just showing a shell. In a shell, the current would look very similar to the infinite helix. Sorry, I meant the field would look very similar to the infinite helix. And the contour you set up would also be the same. Now, two things I want to emphasize. First, how I got the direction, again, by the right-hand rule. You see this current goes out of the page. And if you imagine aligning your thumb to the current, your fingers would align with the field. That's one thing. Second thing is that actually the fact that I said this and this are very similar, this is kind of an approximation, right? Because in this case, this is really a sheet of current. In this case, we're pretending that our field looks like it's a sheet of current and that it doesn't see those individual wires, right? And this is what we discussed a bit in tutorial 8. In section 4.4, there is a discussion about toroidal helices. Those are similar to axial helices, but they're instead wound on a toroidal form. So you would imagine this donut-shaped object, and then there is a wire that's wrapped around it, and there is a current, wrong pen, color, there you go, current that is passing through this wire. The trace would look like this. Here you see coming out of the page are these wires because they are on the inner circle, because on the inner circle J is coming out of the page. Then on the opposite side, the wires are going into the page. The field produced by the torus will be somewhat similar to the field produced by the helix. So it also goes sort of inside the helix. And is zero outside the helix. The way I got this direction, again, is by the right-hand rule. Your thumb would be aligned with the wires, and the rest of your fingers will be aligned with the field. So this is the field F, and outside it's 0. Now, the contour that you would select for this problem is going to be the one that captures the current nicely. So the normal vector to the surface, corresponding surface, would be in the same direction, or would be aligned with the current. You could make it same direction or opposite direction, but you just want to make sure that you're capturing the currents. So this would be your contour, for example, in this direction. You also want your contour to be aligned with the field, right? And this is the normal vector I was talking about. In the same section, there is a discussion about circumferential sheet current flux density that's going around a torus. So it's exactly the same kind of situation. The only difference is that instead of having a helix with wires, you have you would have a surface current that's going on this shell like this. The cross-sectional, well, the trace would look very similar. I just drew these circles here to sort of show that it's a shell instead of individual wires. But really, I could have just copy-pasted the same image because there is really not much difference. The field is also going to be in the same direction, and you would want to choose the same contours. So the field is going like this. Outside is 0. And your contours would be circles that have a surface that captures the current. So circles that go inside of this shell. Here I'm showing a dotted line because it's inside of the shell, so you can't see it technically. You could also have a situation where where your problem is not symmetric, but it's made up of symmetric objects. For example, this problem, one of the objects you have has this kind of current density, so it's axial current density. Actually, let me draw it with colors so that you can see which field is produced by what. Maybe I'll choose brown for this guy. So this is the current. And the field produced is in this direction. Another object you have has circumferential current density. So that's a totally different story, because you can't reuse the same kind of contours for different types of objects, right? For different types of symmetries. So this one has this kind of J, and the field produced is going to be like this. So this would be F1, and the brown one is F2. In tutorial 8, there was quite a lot of discussion about superposition, so you can go back and check what that was all about. And let me show you, in case you're not convinced the contours should be different. You see, this is the contour for circumferential current density. And for the axial current density, this is the kind of contour. Because you want to make sure that your current actually passes through your contour. Otherwise, you're just not going to enclose any current, and your Stokes theorem application would just not give you the right conclusions. Like, it just would be inconclusive, if anything, or you might make a mistake. Let's do problem 12 from section 4.6. This problem involves two objects. One is the slab with cylinder extruded from it. So the slab has a shape like this. And it has J slab equal to J naught S x hat between the two surfaces of the slab, which would be Z equals to D and Z equals negative D. And for y squared plus z squared greater than d squared. What does it mean? This means when the distance from the x-axis is greater than d. So this is outside of this cylinder extruded from this slab. The second object is the cylinder that's parallel to the x-axis. So this would be, well, I'm just showing you like this. This would be this cylinder shown here. And the current density of the cylinder is equal to J naught C x hat when the distance from the x-axis is less or equal than d. Now, these constants J naught C and J naught S, what they are measured in, let's see. This is the current magnitude of the current density, well, the x component of the current density, so it's measured in amps per meter squared. And same thing here. You're told that the field F is equal to 0 when y equals to 0 and when z equals to 2d. This is this point here. So the field F equals 0 at this point, and you're asked to find the relationship between the constant J naught C and J naught S. So this one and this one. The way to do this problem is using superposition. The reason why you have to use superposition is because the problem overall is not symmetric. It neither has cylindrical symmetry nor planar symmetry. So let's break this problem down into a problem involving the slab. So that's the one with the planar symmetry. And you see how I'm filling in the slab? So I'm not extruding the cylinder from the slab. The reason why is because this problem is not symmetric. So the problem involving slab with extruded cylinder. So you have to fill in the cylinder's volume with the current density of the slab, otherwise the field produced will not be symmetric. So this guy, let's call the current density J1. J1 is just going to be equal to J naught S x hat for Z between negative D and D. And this slab is going to produce the field F1. The second problem is the problem involving the cylinder only. Let's call the associated current density J2 equal to some J2 x hat for y squared plus z squared less than or equal to d squared. And this cylinder is going to produce the field called F2. Now, we need to be really careful with what we call this J2. It's really tempting to make J2 just equal to this guy. Just equal to this guy, J naught C. So here, J2 is not equal to J naught C. The reason why is this. If we make J2 equal to J naught C, then inside of the cylinder's volume, when we add the two current densities together, we will get this. Where should I write this? Maybe like this. Well, outside it's going to be correct, J naught S x hat, but then inside, if we choose this, we will get J naught C plus J naught S x hat, right? But that's not what we want. We want J naught C x hat, right? So I'm going to erase this, and I'm going to draw the correct current density. This is J naught C x hat. So we want this J2 plus J naught S x hat to give us this. So let's solve for J2 from here. J2 is equal to, equating the x components, we get J2 plus J naught S equals J naught C, and then we solve for J2 and get J naught C minus J naught S. So then here, we can just write J naught C minus J naught S x hat. And just so you guys have it in your notes, the current density inside the cylinder is, in total, J naught C instead of, J naught C x hat instead of this. Let's find the field from the slab first, and then we'll move on to the cylinder. For the slab, I'm going to use green. Here, I've already shown you the current density. It extends everywhere in the slab, including the portion that's occupied by the cylinder. And the current density is equal to J naught S x hat. Let's make an assumption on the field. We know that the field By the right-hand rule, we would align the thumb with the current density, and then the way the fingers go is the way the field goes. So this would be this way above the slab. And below the slab, it's going to be like this. You see that the field only has a y component, negative y component above the slab, well, assuming J0s is positive, and positive y component below the slab. And also, the y component only depends on the z coordinate because when you walk in the y direction, you see the same picture, and the same thing happens when you walk in the x direction, so this would be into the page or out of the page. But then when you change the height, the picture changes, so the magnitude or the y component of f1 changes as well. This f of z is an odd function. The reason why is because above the slab, the y component is negative, and below the slab, the y component is positive, but then the magnitude of f is the same on both sides of the slab. Let's set up the Amperian contour. This is what we'll use to apply the Stokes theorem. Let's make the contour a rectangle that, remember, we set it up to be a rectangle in a way that captures the current density. And let's make the let's make the contour pass through the point where we were told the field, because in the end we want the expression for the field at this point. Let's orient the contour this way. And then here, so this would be contour C, and we can also break it down into 4 portions. Well, okay, you know what? Later, when we actually integrate, I'll do that. What else? We also know that the contour, by the right-hand rule, since we oriented the contour this way, the surface is going to be oriented like this. Again, fingers will align with the contour, and then the thumb will show you the direction of the corresponding surface for applying the Stokes theorem. I'm going to label the surfaces, the portions of the contour. Here would be the contour, the y value equals to y1, or we could also call it negative y2, where y2 is the y coordinate of this portion. You see, I'm just making the contour symmetric. It doesn't really matter if I make it symmetric with respect to y equals 0 or not, but it's convenient, so I'll do that. Z here equals to negative 2d. You see, I'm making it symmetric, this contour again. You'll see in a minute why it's a convenient choice. And then here is z equals 2d, as we just discussed. Okay. Let's evaluate the left-hand side of the Stokes theorem. Here, this is the contour integral of the field dot ds. This can be broken down into 4 integrals. You see there the integrals corresponding to each of the portions of the contour. You see this is y equals negative y2. This is this vertical part. Y equals to y2. This is this part. And then z equals negative 2d, this part, and z equals to 2d. This is this part. Now, this contour and this contour will have the integral 0. The reason why is this. On this part of the contour, ds is oriented downwards, right? And the field is oriented in this direction. So we have, let me show ds. ds is this way. So then we have the angle between the two vectors equal to 90 degrees. When you take a dot product, you get 0. So then this dot product is 0. The same thing happens for this contour. So then these two integrals cancel. Well, not cancel, they're just 0. And we're just left with these two integrals. This is what I'm writing here. Now we just want to simplify these two integrals. These would be the one for this contour and this contour. On the bottom contour, f equals to f at z equals to negative 2d y hat. Here I just plugged in z equals negative 2d and this y hat here. For the top contour, we have f at z equals to 2d y hat. Here and here I just copied these expressions. I plugged everything in. Then the next thing I did is this. I realized that for the bottom contour, we have y hat is going to the right. Let me just write it here. So c negative, for the contour c negative 2d, we have y hat, sorry, we have ds, oh no, y hat dotted with ds. This is equal to magnitude of y hat, magnitude of ds, times cosine of the angle between the two. On this part of the contour, ds is going to the right, same as y hat, so we get this times 1. For the top contour, c2d, we have y hat dotted with ds equal to 1 times ds times, now we have ds is going to the left on this part of the contour, and y hat is going to the right, so here we get negative 1. So then this for the bottom contour is plus ds, and this would be minus ds. On this line, I just plugged this in. This is the same as this. On this line, I just took this minus and took it out of the integral. The next step is to take this part. This is just a constant, right? Because it's some function of z, but it's already been evaluated at z equals negative 2d. So then this is a constant and it can come out of the integral. Now here I'm using heavily the symmetry of the field because I'm using the fact that the z component of the field is a constant everywhere on this contour. If the z component wasn't a constant, I wouldn't be able to take it out of the integral. Then I do the same thing for this guy, and I'm left with a constant times an integral of differential length element over this bottom contour. So then I just need to take, what I need to do is to get the length of this contour. The length of this contour is equal to, well, this is negative y2 and this is positive y2, so we get 2y2. And same thing for this guy. So then I evaluate the integral for this guy and for this guy, and then I get this constant, this one, times 2y2, and then the same thing for this part. The next thing I did is this. We don't want, so we like this guy, f at z equals 2d. The reason why is because the field in question is right here. But then z at negative 2d is not what we want. But we know that z at negative 2d is negative fz equals 2d. This is because, first, f is an odd function, so then this is just a property of odd functions. Another explanation is that we have the y component flips sign on these two contours, so one is the negative of the other. Then plugging this in, we get this. So I just wrote 2 times this guy, and this would be the left-hand side simplified. Now let's do the right-hand side. On the right-hand side, we have the flux of the current density through the surface that's defined by this contour. Now, there are infinitely many surfaces, but let's choose the one that's flat because it's the most convenient one in this particular case. So then we have what? We can integrate this current density over dz and dy. So this would be our surface element, so the scalar surface element. But then this guy has direction, right? So then to get it with the direction, what do we add? We've determined that we want, by the right-hand rule, we would want n hat to be in the direction of x hat, right? So then the direction part of this ds is x hat. Oops. So then this whole thing would be ds with the vector. Now the integration bounds would be from negative y2 to y2, which is just the bounds of this contour in terms of y. But for the z bounds, we need to actually be really careful. You see how here I wrote this, which is the expression inside the slab. Because I wrote this, I have to write here, instead of writing negative 2d to 2d, I have to write negative d to d, because this is the only part where j cylinder is equal, where j slab is equal to j naught s x hat. Everywhere else is 0. I think we've done this kind of argument before, but just in case, I'm gonna repeat it. Okay, so then if you do want to write this from negative 2d to 2d, then here you would need to write something like this. So aside if you want the bounds to be like this, so the bounds of the entire surface, then here you can't write j naught s x hat. You'll actually have to write more accurately something like this: j naught s x hat for z between negative d and d, and then 0 elsewhere. And then the very next step is just going to simplify to this integral. So there is no point actually writing it like this. We can just write like that, but just be really careful to put these bounds correctly. Okay, so here I've just copied everything, and what I also did is this. you see this x hat dot x hat, that's just 1, correct? This is 1, that's why it just disappeared here. Next, let's integrate over y. We get 2y2. This j naught s is out of the integral. Integration over z will give us 2d. Then what I did is I equated left-hand side and right-hand side and solved for f1. Let me show you. This is the left-hand side. It's right here. The right-hand side is from here, just copied. Then I canceled a bunch of things. For example, I canceled this. I also canceled this too. And then you see on the left-hand side we have negative of the y component of the field. So then flipping the signs on both sides, I got negative and then j naught s times d. So now we have the y component at this height, everywhere on this height, which lets us find the field at this point. We can use this expression that we have. So we have f1 equal to f at z equals to 2d, y hat equal to negative j naught s d y hat. Okay, that's it for the field from the slab. Now let's find the field from the cylinder. The field from the cylinder, let's assume it to be in this sort of form. The reason why is because by the right-hand rule, this will generate the field that goes something like this. And the symmetry of the problem tells us that the field is in the theta hat direction, and the theta hat component depends only on the distance from the x-axis. So this would be distance from x-axis. Now let's set up the Amperian contour. Now this part I'll actually go through quickly because I was told that you've already done this in class. So, okay. So Amperian contour that we want would go through this point because that's where we're told the field. Well, the total field. So we'll make the radius of the circle equal to 2d. Let's orient contour like this. By the right-hand rule, then, the direction of the surface is like this. The left-hand side of Stokes' theorem simplifies as follows. We have f2, remember it's equal to f at r, well actually r equals to 2d times theta hat. I'm actually going to replace this with 2d. And then we have this. We have theta hat dotted with ds. Theta hat is in this direction. ds is also in this direction. So then we have the two things when you take dot product. We get magnitude of this times cosine of the angle between the two. So then this is equal to f at r equals to 2d times everything that's left, and this is equal to f at r equals to 2d times the circumference of the Ampérian contour, 2 pi r. And remember, r is equal to 2d. So this is the left-hand side. On the right-hand side, we have, again, the flux of J through the surface. So we have, let's integrate in cylindrical coordinates. We'll have theta going from 0 to 2 pi. R, well, we need to be careful here. You see that this is not, well, this is applicable only inside of the cylinder. It's the charge, sorry, the current density is 0 everywhere outside the cylinder. Then this means that R needs to go from 0 to D. Then for ds, we have the direction of ds. Remember, we chose n hat to be in x hat direction. And then we have the differential surface element, which would be r dr d theta. And don't forget this r. Remember, this is a differential surface element, which needs to have units of area. If you don't put this Jacobian, you will get incorrect units. You would get meters times radians, but you want meters squared. Now, this is not a justification for the Jacobian being precisely that, but you can derive that this is the Jacobian. But I'm just explaining why you shouldn't forget it. Okay, here I copied everything I just explained, and I also simplified x hat dot x hat to be 1. Next thing I did, I took this guy out of the integral. This is here. I integrated over theta. The integral would be 2 pi. And then we have integration over r. So we have integral 0 to d of r squared dr. Sorry, of r dr, which gives us r squared over 2 from 0 to d. And this is what I wrote here. D squared over 2 is what you get. And then also we can cancel a bunch of things. You see there is this 2 here and 2 here. Then we get j naught c minus j naught s pi d squared. Next part is the equating left-hand side and right-hand side and solving for the field at this point where we want. Left-hand side, sorry, is this. You see f at r equals to 2d, I wrote here, and then we have 2 pi times 2d is here, equals to this whole expression I just copied, and then I canceled this d. I also canceled pi, and then I combined this 2 and this 2, so I got here, this would be 4, and then I divided both sides by 4. So then I'm left with this guy, which is this, times d divided by this 4, right here. Okay, so this is the expression for the theta hat component because of the vector field. When the distance from the x-axis is equal to 2d. So everywhere on this circle, well, cylinder, our f equals to this guy, f at r equals to 2d times theta hat. So then we get j naught c minus j naught s d over 4 theta hat at this particular point. Now, it's not everywhere, right? It's only when distance from the x-axis is equal to 2d, right? Okay, so this is that, but you see there is this theta hat. We don't like this because in the previous part of the question, we got everything in Cartesian coordinates, and this theta hat is going to be difficult to add to something in terms of y hat. So let's convert this to Cartesian. We know that at this point, which remember is x, 0, and 2d, at this point, sorry, what am I writing? We have theta hat equal to, let me just label the axes, theta hat is equal to negative y hat. So then this guy is negative j naught c minus j naught s times d over 4 y hat. Now let's add the two fields together, get the expression for the total field, and then solve for the two unknowns that were asked for. Here I just copied everything I wrote before, except with mistakes. Oh no, I'm so sorry, this should be y hat. I'll fix it in the actual notes. Okay, this is y hat. Okay, I'll fix it. I think so basically your notes have the correct version. You don't need to correct anything, I hope. Okay, and then we want to add the two fields together. We get this, and then you see this negative, it can come out of the sum, and then this, well, y hat is right here, and then this is here. Should be using black too, because it's the total field. Okay, so this part is here, and then this part is here. Remember, we were told that this is 0. The only way for this to be the case is for this whole thing to be 0. That's what I wrote here. Then I took this and transferred it to the right-hand side. That's what I got here. Next thing I did is I multiplied both sides by 4. So I got this. And then, oops. And then I transferred this to the right-hand side. So then I got negative 3 here, because it's negative 4 plus 1. And this is it. This is all we need to do for this problem. Since we still have some time left, I want to talk about one more thing. Remember, in the problem we just did, there was a part about finding the field due to the slab. At this point. So this was outside the slab, and we found that the field here was equal to negative j naught s dy hat. Well, it turns out if you were to do the calculation for some arbitrary z value above the top surface of the slab, you'll find the exact same field. I'm not redoing the calculation, but it's going to be exactly the same as we just did. So this is the field here. The field below the slab is the same, but just in the opposite direction. So we have F1 equals to plus J naught S D y hat. What I want to show you now is how to find the field inside the slab. To do this, we want to set up a contour in such a way that at least, well, that one of the lines passes through the slab. Otherwise, we don't have any hope of finding the field inside the slab. Let's orient the contour this way, and let's make, and then by the right-hand rule and hat is this way. Let's make this side at negative 2D, since that's where we found the field before. Well, we found it here, but it's symmetric. So we have this as well. And we also have it everywhere else below the slab, but that's okay. Above the slab, we have, sorry, on the top line, let's make this at a height Z2, and let's just keep it arbitrary. Since we don't know what it is, we want it everywhere inside the slab. Okay, now let's simplify the left-hand side of Stokes' theorem. Again, we break down the integral into 4 parts, but only the parts parallel to the field survive. So this would be the one for the bottom surface, the bottom line and the top line. What I did here is I wrote F1 for the bottom line as what we just found it to be, J naught S dy hat. And here I wrote it as some function of z evaluated at z2 times y hat. What this is, it's the y hat direction and then the z component. Remember the notation we were using before, how we're assuming that f1 is some f of z times y hat. This is what I wrote here. Then in the next step, I simplified y hat dot ds. So we have c at negative 2d would have y hat dot ds equal to 1 times the magnitude of ds times plus 1 because they are parallel. Here we would have this should be z2. Y hat dot ds is equal to negative ds because ds and y hat are in opposite directions. Then I took this part out of the integral, and I'm left with this. This also goes out of the integral. That's what I got here. For this part, we have the length of the contour, which is equal to, again, 2y2. Because remember, we're making our rectangle between some value y2 and negative y2. Now for the right-hand side of Stokes' theorem, we have, again, very similar integral as we did before. This is our ds vector. dz dy is the differential surface area, and this is its direction. This is the value of J1 plugged in. Remember, J1 was J naught S x hat as long as we are inside the slab. Then for the Z values, we're going to only integrate over the part of the slab where there is current. So this would be between negative D and Z2. The next thing I did is I took x hat dotted with x hat. This was 1. This is what I got here. And then I integrated, and I got J naught S is a constant. Integration over y gave me this, and integration over z gave me z2 plus d. Then I equated left-hand side and right-hand side. The left-hand side is shown here. This I copied from here. The right-hand side is shown here. Then what I did is I canceled 2y2. And then I took this and transferred it to the right-hand side. And I also took this and transferred this to the left-hand side. So then I have this minus here from this, and this goes with a plus. Then I did the following. I expanded this as J naught S Z2. Well, I'm going to include this minus. So minus, and then minus J naught S D. And this cancels. So I got this F at Z equals to Z2 equal to negative J naught S Z2. This means that at an arbitrary x, y, z inside of the slab, we have F1 equal to this guy, with z now being just some arbitrary variable, and with the direction added back to it.